Hey, I'm Dr. T and welcome to my office. So today I'd like to talk about buffers. So buffers are a mixture of chemicals, it always has to be at least two, that are going to resist the change in pH. So if you add acid to a buffer, then your pH will go down, but nowhere near as much as it would have if the buffer wasn't there and you're adding to pure water. Likewise, if you were to add base, the pH will go up, but nowhere near as much if you had simply added that to pure water. Okay, these seem like they might be useful because remember, lots of systems require a very constant pH, especially if you've got things like proteins and enzymes and those kinds of things that are very pH sensitive. And there are other chemical reactions that are completely abiotic that still require very precise pH control. So this seems useful. How does it work? Well, the core of a buffer is going to be a weak acid and a weak base. Specifically, I should actually say that the weak acid and the weak base are what we call a conjugate pair, meaning that the acid and the base are basically the exact same chemical, except for the acid has an H+ hook to it, and the base does not. The conjugate acid of a weak base, or really of any base, is going to be that base, but it's now the product after it has picked up the hydrogen. The conjugate base of an acid is going to be the acid after it loses the hydrogen. It's now the product, and it's no longer having the hydrogen attached to it. And with that, we're setting up an equilibrium. So I have a weak acid or a weak base, and I have its conjugate. If I am to add acid, what I'm going to do is drive the chemical reaction. I'm going to do full-on Le Chatelier, and I'm going to drive the chemical reaction to the side that has the acid with the proton attached. This means that when I add acid, most of my protons that come from the acid that I add aren't going to go hang out on water molecules, at least not for any meaningfully large period of time. Instead, they are going to be attracted to one of the weak bases. They're going to attach to that, and therefore have no effect on my pH because they're not on a water molecule. Likewise, if I add a base, then it's going to pull H pluses off of my water molecules, but those will then be replaced by the weak acid. Thereby, I'm stabilizing my pH. There's a multitude of chemicals that can be used as a buffer. In reality, you really can use any weak acid or weak base so long as the pH that you have is at a point that's relatively close to its pKa, or the power of its equilibrium constant for it being an acid. Now there are several popular choices though. Phosphates are a wonderful one since they actually have 3 different protons, therefore 3 different pKa's and 3 different pH ranges they can function at. Typically speaking, a buffer works within about, give or take, 1 pH unit of its pKa, which is a property you can look up online from a multitude of sources. Now, with humans, we've got tons of buffers. One of the most important is going to be the one that keeps our bloodstream a nice 7.4 pH. And that is going to be a bicarbonate-based buffer. The way we actually control this is kind of interesting. You got a couple of organs that play a fairly major role. Your kidneys obviously are controlling what's in your bloodstream. But surprisingly, although not so surprisingly if you think about what that buffer is, your lungs play a major role in pH control. Keep in mind that's a bicarbonate buffer. What happens when I take and add an acid to a bicarbonate? That's right, I get carbonic acid, which spontaneously turns into carbon dioxide. What do I exhale? Carbon dioxide. So by your lungs controlling how much carbon dioxide is in your system, they control your pH. Useful. If you're wanting to make a buffer, you've really got about 3 choices on how to make this. Obviously, you have to go look up a chemical that has a pKa fairly close to that of the pH you want. Once again, give or take about 1 pH unit. Although, actually, if you look at your blood's buffer, that's not exactly 1 pH unit away from the pKa of bicarbonate. So, you know, you can go further, but not recommended. So you can take your desired chemical, and you got really kind of 3 choices. One, you take your weak acid or weak base, you hook it up with a pH probe, and you just start adding strong acid or strong base, whichever one you need, you know, would be the opposite. And thus you just keep adding until you hit the desired pH. The amount of buffer weak acid or weak base that you add will determine how much it's able to buffer it, what we call buffering capacity. The more weak acid and weak base you have, the more it can resist pH change. It's optimal right next to its pKa. As you get away from that, then the buffering capacity starts going down. That's why you don't want to get too far away from the pKa, because you just don't have enough of the weak acid or the weak base present to actually have a meaningful impact on the pH. It doesn't really work that well when you get too far away. The second choice, you can use the Henderson-Hasselbalch equation, which relates pKa and the concentration of H+, in order to tell you the ratios of the weak acid and weak base that you need. Although that's not my preferred method, because that's a lot like work. So instead, my preferred method is you look up a buffer table. Yeah, people have been making buffers for a while, and some people have put them in books and published them, or put them on the internet. And so if, hey, I want a phosphate buffer at pH 7.2, I just go look up what mixture of phosphates do I put in my buffer, and then that way I just have to mix my chemicals and I'm done. So that one doesn't get as much press as the other approaches. I don't know why, because it is super practical and incredibly useful. So with that said, if you are working with buffers, have fun. Go find a good buffer table for you. And I will see you in later videos. Have a wonderful day.